We measure our planet's extremes by the jagged peaks of the Himalayas. Mount Everest stands as the absolute limit of Earth's vertical reach and exploration. Its summit cuts into the stratosphere at just over 29,000 feet above sea level, reaching an altitude where the atmosphere is so thin that oxygen deprivation begins to shut down the human body. This colossal mass of rock is actively forced skyward. Deep in the middle of the continent, the Indian and Eurasian tectonic plates are locked in a slow-motion collision, violently buckling the crust upward over millions of years. This topographic map shows the complex ridges of the Himalayan range, representing millions of tons of elevated rock pushed upward. Yet, compared to the rest of the solar system, Earth's mountains are severely stunted. Earth enforces a strict physical ceiling. A set of specific planetary laws prevents our mountains from growing infinitely tall, pointing to a much larger mystery about how planetary physics govern geology. In 1971, the Mariner 9 spacecraft arrived in orbit around Mars. The planet was entirely engulfed in a global dust storm, obscuring the surface from the camera lenses. As the dust finally began to settle, the first features to pierce through the planetary haze were the peaks of an impossibly high mountain. This topographical map shows Olympus Mons, the tallest planetary mountain in the solar system. The black outline demonstrates its 600-kilometer width, superimposed over New Mexico. From the surrounding plains, elevation to the central caldera approaches 27 kilometers, making it 3 times taller than Mount Everest. Mars and Earth are both rocky terrestrial planets, so what physical rules restrict mountain growth on our world, and how did Mars completely bypass them? The first constraint is the sheer physical weight of the rock itself. Mountains contain an enormous amount of mass, and Earth's gravity pulls down on that mass with about 2.5 times the force it does on Mars. When an Earth mountain reaches a certain mass, gravity actively begins pulling it back down into the crust. The pressure at the bottom becomes so immense that the rock forming the base actually begins to melt. The mountain is forced to spread wider along the crust instead of growing taller. Mars exerts a much weaker gravitational pull. This effectively removes the structural tax, allowing molten rock to stack higher and higher without collapsing under its own weight. To understand how a mountain forms across those vast heights, we look to Mauna Kea in Hawaii, Earth's tallest mountain from base to peak. Like Olympus Mons, it is a shield volcano. Shield volcanoes do not erupt explosively. They are built over millions of years by highly fluid basaltic lava that spreads steadily over vast distances before cooling, creating broad, gentle slopes. But on Earth, our tectonic plates constantly shift. Earth's moving crust slides over stationary magma hotspots like a conveyor belt, creating a chain of smaller islands. Mars lacks this horizontal movement. Its locked crust continuously fed the exact same peak for hundreds of millions of years. Recent analyses of orbital mineral data, published in 2026 by a team led by Bartosz Pieterek, have provided a detailed look at this erupted history. These mineral signatures revealed a history of highly complex, evolving magma systems that were stored deep beneath the surface over vast periods of time. While the crust didn't slide horizontally, the region experienced vertical tectonics, where the land shifted up and down, fueling these long-lasting volcanic giants. A stationary crust, paired with an incredibly active, evolving magma engine, provided the exact conditions needed for limitless vertical growth. Even if a terrestrial mountain could survive gravity and tectonic drift, it faces a final, relentless limit: Earth's plentiful water. Rainwater runs down slopes, washing away material grain by grain. Water seeps into cracks, freezes, and expands, breaking off slabs of the mountain. At higher altitudes, snow compacts into massive glaciers. These rivers of ice act like slow-moving natural bulldozers, carving deep valleys through mountain ranges and grinding away the rock, strictly papping their ultimate height. Mars operates under entirely different atmospheric conditions. Today, it is a freezing, dry desert, completely devoid of flowing liquid water. Once the lava flows on Olympus Mons finally cooled and hardened, there was no rain or glacial ice to tear the rock back down. Untouched by the erosive forces that dominate our planet, Olympus Mons stands today as a perfectly preserved fossil of an ancient geological era. The physical profile of a planet's surface is a direct record of the internal and external forces acting upon it. Olympus Mons grew to its staggering proportions precisely because it exists in an environment with weak gravity, a geologically locked crust, and a lack of flowing water. On the other hand, Earth's shorter peaks serve as a visible record of our planet's highly dynamic and active environment. The exact forces that continuously cap our peaks, the shifting tectonic plates that recycle carbon, and the rich water-filled atmosphere that erodes stone, are the exact same systems that make Earth a living, habitable world. Olympus Mons remains a magnificent, silent monument to a planet that stood still. Earth's modest mountains are the structural proof of a planet in constant, life-giving motion.